And up next we have Tiffany, who has to time her own talk.
Yes.
But talking about circumbinary, or talking about disks around
Yeah, circumplanetary
disks.
I promise I'll try to stay to time. Yeah, if you tap, yeah, you got it. Okay, I'll just get started. So for those of you who know me, you know I work on exoplanet high contrast imaging and coronagraphy, and this is not my area of expertise. I'm more aligned with the coronagraph instrument, but I wanted to think of like what's something that I find really interesting that we'll do with WFI that I think is people are not really thinking about so much, and I'll tell you about that in this talk. So this is just to remind you, how many exoplanets have been detected through all the different methods, and I'm going to focus on the transiting planets, just to give you a sense. There's thousands and thousands of planets that have been found through the different surveys, and there's a lot that we learn from these transiting planets. So as you know from our previous talks, when you have a transiting planet, you have a planet that passes right in front, and you see the brightness of the star dim. And there's a lot that you can learn by looking at this light curve, right? So you can understand things about the atmosphere of the planet, you can understand the radius of the planet relative to the radius of the star, you can understand its orbit. So there is really a lot of interesting information that you gain. But what if the planet has rings? When I say rings, I mean, let's say a circumplanetary disk. But for the purposes of this talk, to make it sound more interesting, I'm going to call them exorings. So how can we spot this in our light curves? Well, if the planet itself, seen here in the center, has a disk or exorings that are of order the same diameter as the star, you'll see basically an asymmetric light curve here. So you'll see kind of an unusual dip. If the disk is larger in diameter, angular diameter, than its star, you will still see an asymmetric dip, but it will have a slightly different shape. And then in the very unusual cases, the most unusual cases, where you have a very, very large system, you will actually be able to see the structure as the star, well, as the system, the disk and the planet pass in front of the star. You'll see actual dips from the rings itself coming in and out of the transit. Now, just to give some motivation for why we might be interested in this, all of our outer four giant planets have some rings of some sort. So there is some kind of context for this in our own solar system. And just to give you a introduction to kind of the most exciting and unusual giant exoring system, I'll introduce you to J1407. So about in the early 2010s, a graduate student, Mark Picot, was working with Eric Mamajak. And they were trying to get all the information they could on the SCO-SEN stars to really nail down their ages and all the properties of those stars. And they found an unusual star that was basically trucking along pretty flat for many, many years. And then all of a sudden, it just started having extreme transits and occultations. And you see that in the middle of its eclipse, it literally disappeared off the image. It was too faint. And then it suddenly jumped back up again, and then had a very strange structure over 56 days. Okay, extremely unusual system. So what is this? So the team thought about this a lot and considered lots of options, and the kind of best option that they could find in the end was that this is a planet that is surrounded by a very large ring system of diameter 1 AU at a very large separation from its star, and you're seeing its transit right in front of this star. This is a nice video which shows essentially how much detail there is from this light curve. You can see how well this fits to each of the rings as the star passes in front. Well, as the ring passes in front of it and it comes in and out of this eclipse, then you see where we lose information because it's just too faint, so we don't know exactly what's going on there. And then it matches pretty well. You'll see it's not a perfect match, but it's a pretty great match for you have symmetry on both sides of this whole ring system. Okay. How many of these giant occulting exorings have been found, you might ask? Well, 3. So not a lot. One is J1407, as you've seen. There are 2 more. This is all we've found so far from detailed searches of many different surveys. Essentially, you know, this is all the information we have so far in these giant systems. Remember, the giant systems are the ones where the disk is so much bigger that you can actually see structure in the rings as they transit the star. What about compact occulting exorings? Also 3. This is how many that have been found. So a team went through all of the Kepler K2 data, and they were looking specifically for these asymmetric transit signatures, and they found 3. These are compact systems, so that is when the disk is roughly the same diameter as the star. So you're not seeing like the detailed ring structures, but you are seeing this asymmetric transit. Yeah, so basically, this is how many that have been found so far. And these, by the way, these transits are of order of a day. Okay, so this brings me to Roman. The Galactic Bulge Time Domain Survey will be an incredible resource for finding exactly these systems. And the reason is because it will be monitoring 60 million stars towards the galactic bulge. In the Kepler K2 data for reference, it's about 500,000 stars, so this is a significantly larger sample of stars. It will have 70 days of continuous viewing per season of a 12-minute cadence. That's absolutely fantastic for this type of science because, and this is the kind of magnitudes we think we'll be sensitive to, because we'll be able to find these compact exorings, which are on orders of hours to days of transits with the very short cadence. And we'll also be sensitive to these giant exorings, which are of order days to weeks, which would be otherwise missed on other surveys that just don't have a long enough continuous viewing season. And also, because we'll have such short cadence and such a long period of time, we should be sensitive to these sharp ring edges and gaps in these systems. So how will we find them in these data? Basically, as the disk passes in front of the star, you'll see this asymmetric transit. And so essentially what we're looking for is a sharp ingress and a gradual egress, or the opposite. And in terms of the analysis, what are we going to do? So we're planning to use as a kind of a first pass the photometry and light curves that are generated by Roman, so without redoing all of the light curves for 60 million stars. We cannot do it by visual inspection alone, as has been done for all the other ones that have been found. We certainly cannot go through 60 million stars. So first we'll do some pre-filtering to remove things like bright saturated stars, known variables, things with insufficient photometric precision. And then we'll do an automated detection, so like a sliding window algorithm, which is similar to what has been done for finding exocomets in Kepler, to intentionally find these asymmetric events. And then we'll do some kind of validation. So I think this survey primarily is in this filter, but some data we'll have, we will have on a longer cadence, we'll have some other filters. So where possible, we'll use the other data, but otherwise we may do a manual inspection and, in some cases, re-extract a new light curve. So what might we learn? Well, how common are these exorings? Are we finding many of them? It's really hard to predict how many we expect to find. I have a little video here just to show that, exorings and circumplanetary disks are a predicted byproduct of giant planet formation. But there have not been very many found so far. Our ballpark estimate of how many we may find is roughly 50 to 1,000 exorings in this survey. This is super ballpark. I can tell you a little bit more about how we came up with that number, but it's hard to know exactly how much we'll find. But we know we'll find several, probably several dozen, maybe even hundreds. we hope to find what these rings are made of, so we have some multiband data, but most likely we'll do spectroscopic follow-up to understand the disk composition a little bit better. How long are these exoring lifetimes? Theory suggests they're quite short. So, this will be important to understanding the number that we actually find in terms of how long their lifetimes are. And then how do these rings form? Are they from scattering interactions from other gas giants? There's a lot of different theories that potentially we could rule out by having a larger sample size. Okay, so as I said, we are definitely going to find many exoring systems in the galactic bulge time domain survey. I don't know how many, but it will be very exciting. It will be certainly a very large number. And even a few dozen detection events will greatly increase the number of exoring systems that we have. And they will help us understand how giant planets form, how exorings form and their lifetimes, and it also sheds light on the planets in our own solar system and their rings. And I just wanted to end with this nice image. This is a building in Leiden, and this is Saturn if it had the rings of J1407. This is what it would look like. So it's so large that at sunset you could see it by eye. That's it. Thank you. Thank you.
All right, thanks. That was great. That was really fun seeing all the one of the many exotic things we'll find with Roman. Yeah. Questions for Tiffany? I see a question from Ward.
You were mentioning spectroscopic follow-up, but I was wondering, even from the multiband data that you have and the slow timescales of these events, if you could start to place constraints on particle grain sizes and compositions.
Yeah, definitely. I think, that's a very good point. So, wherever possible, we will. I think the plan for this survey is I don't think the 12-minute cadence is with every filter. It's just with one filter, I believe, and then those two other ones that are on like a 12-hour? Or
every 3 hours you get another filter, okay. But they're offset by
exactly, 3. Yeah. So we'll use whatever is available, absolutely, yeah. But they won't all be on that same cadence, yeah. But you're right, yeah. Yeah, oh, absolutely, they will last that long. You're right, yeah.
Okay. I see a question here from Robbie.
Hi, so I was just wondering, if you had like multiple events from the same ring system, do you expect the structure to be persistent, like on orbit timescales?
Yeah, well, so I will tell you some surprising information that almost none of these systems have a repeat transit. So that makes them somewhat uncertain, let's say. But yeah, I think the idea is that probably the structure would be similar on a similar orbit, but the idea is that they all have such long orbits. Like J1407 was detected in 2007, and we've not seen it transit again. These transits have to be very, very far in order to maintain a disk of this size without being torn apart by the star itself. So it's on at least a 19-year orbit. It could be more. I don't know is the answer. I do hope we get multiple transits for some of these systems. And that's one of the strengths, again, of Roman, is that we'll be revisiting this same field over and over every year, right, for 70 days. Hopefully we will actually see more repeat transits and learn more about that.
And once we've got 2, then we'll have an extended mission on Roman to go and measure the additional ones.
Yes.
Okay, any more questions for Tiffany? I don't see any, so all right, thanks, that was very interesting.
Thank you, everyone.
All right.